Okay, on to chapter 6 questions, starting with the easy questions in Statistical Rethinking, second edition. I've just kind of combined 6E1 and 6E2. Um, and so the idea is that we need to list some mechanisms. It asks for 3. I think I listed 4 or 5. List the mechanisms by which multiple regression can produce false inferences about causal effects. And then the second one is to give an example from your own research. And so I've just given some examples as we go along. So let me, I'm not going to go through every single one here. You should go to the Colab sheet and you can read my answers. This is just a lot of text and not much to talk about. I'll talk about a couple things, but I want to first expand on this question a little bit. So the question specifies talking about inferences about causal effects, okay? And this is a very important distinction. So when we're running something like regression, or really, a lot of different statistical analyses, what we are, we could be interested in trying to make inferences about how the different variables are causally related, how X affects Y or whatever. But there's another completely legitimate use of these types of analysis methods, and that's simply to predict things. And when we want to predict things, then the things that are false inferences about causal effects does not necessarily mean that it's going to make the prediction worse. Okay, that's not the case. So I won't expand on that. It's discussed more in the book, but that's just an important distinction to make. Okay, so some of the mechanisms that are discussed here in the book, I've bulleted here and put and bolded them so you can identify them pretty quickly. And so, like I said, I'm not going to go through every single thing here, but I'm going to highlight a few things. The first thing I want to highlight that is not really discussed in the book, but I think is very interesting, and I'm not going to give a proof here, but there are proofs out there that are kind of illuminating, and that is with omitted variable bias. Okay, so omitted variable bias means that say that we have a regression model where Y is being regressed on alpha, but the predictor variable for Y is X. Okay, that's what we're regressing on. But in reality, there is another causal factor here that's important, and that happens to be W. Okay, so our regression should have a beta W term, but we, for whatever reason, did not consider it or whatever. So our regression will only estimate alpha X or beta for X and the epsilon, which is the error in the model that we, quick aside, in the models that we've been using, we don't use this epsilon. It drops out for reasons that aren't important here, but I'm just putting it here for illustration purposes. Well, just because we didn't include W in the regression does not mean that its influence is not actually there in the data, is not actually there in the values of Y. So where did that influence go, right? Well, if W is completely unrelated to X, then all of that influence of W gets shunted then into the error term, okay? Well, partially into alpha. I should have omitted alpha to make this more clear, but it gets shunted into the error term, okay? So that just means that our predictions will be worse because this epsilon term, this error term, is going to be bigger. That's fine. But if X and W are somehow related, right? If they're sharing some information, right? If X goes up and W goes down in the data, for example, for whatever reason, well, the extent to which they are, the extent to which they're sharing information, or the extent to which W and X are associated, that causal effect of W on Y is going to be soaked up by the beta term for X. And so by omitting W, it will seem as though that some of the effect of W will be represented by, we will think that it is the effect of x, okay? And that will, again, that will be to the extent that w and x are related to one another. That doesn't get expanded on the book, and so I thought I would expand on it here, okay? The next thing I want to point out is that these remaining examples here, post-treatment bias, collider bias, and confounding, are all taken, or are all consequences of the motifs, these causal motifs that are presented in the book. There's actually a fourth motif, which is the descendant, and it can take on the features of any one of these forms, depending on whatever. But read the book for that. So this post-treatment bias it comes from mediators, or pipes, as they're called in the book. So a post-treatment bias would be something like X is a treatment, Y is the outcome, and X affects Y via M. And whenever we are conditioning on a variable, which means we include it in the regression, then it is as though we are holding a value constant. In this case, if M is in the regression, we are holding M constant. Okay, well, in order for X to cause Y, it means that when I change the value of X, the value of Y changes. But if changing the value of Y runs into this wall where I'm holding M constant, right, then all of a sudden the influence from X to Y is halted, right? And so that's a post-treatment bias. Okay? Confounding is discussed, or forks forks produce confounding, right? So if I have that X does not cause Y, but instead they are both a consequence of F, for instance. If I have a regression of Y on X, well, then that's going to look as though X is associated with Y, and if we believe that X is a cause of Y, I will believe that that association is because of X causing Y. But actually, the reality of the situation will be that F is causing both X and Y, right? Because there's an association going through these arrows. And so the only way to stop that association is to condition on the middle variable here, in this case F. Okay? So notice then that in mediators and forks, conditioning on this middle variable, whether it's M or F, blocks the association between X and Y. Okay? Now in the effect of mediators and pipes, that might not be desirable, right? We actually want to see how X affects Y, and so conditioning on M will block the will screw up our inference, right? Because it blocks the association between X and Y. However, in forks, we do want to condition on this middle variable, right? If we want to know the effect of X on Y, and there is no effect, well, the way that it's going to be revealed is if we condition on F. Okay. Now colliders differ. Okay. Colliders differ because when we condition on this middle variable here, C in this case, I'm calling it C. Let me back up. In the case of a collider, X and Y are not associated. They have no association when they're looked at alone. But when I then consider C, I open this flow of association between X and Y. And again, if I'm hypothesizing that X causes Y, and I condition on C for whatever reason, I will open up an association between X and Y. And therefore, it will seem as though X causes Y, if that's part of my hypothesis, right? The results will support the hypothesis that X causes Y because I have conditioned on C, even though X is not causing Y. Okay? And so when this is taking place, then what we have is a collider bias. Okay? And the book has a few good examples. So that's all I'm going to say here. I just tried to expand on some points that I thought maybe weren't super well covered in the book or just kind of glossed over. But that is it for this one.